This is the first video on Chapter 22, Rank, Nullity, and Orthogonal Complements. So this is a very long chapter. What I want to do is just go through and hit the major highlights in this chapter. Now, in everything that I'm writing here, A is an M by N matrix. So it's going to have M rows and N columns. So keep that in mind as you read everything. This is all in reference to A being an M by N matrix. So the rank of the matrix is the dimension of the row space, and we usually write that as a little r of A. The nullity is the dimension of the null space. So that's what the nullity is. Also, the dimension of the row space and the dimension of the column space of the matrix are the same. Now, that's not to say the two spaces themselves are the same. In fact, they may not even live in the same Euclidean space. So the row space of the matrix lives in Rn because the matrix has n columns, and the column space of the matrix lives in Rm because A has m rows. So these two spaces, the row space and the column space, are not necessarily the same space, but they do have the same dimension. And that dimension is called the rank of the matrix. Okay, another thing to keep in mind is that the row space and the null space are orthogonal complements of each other. I did not put the definition of orthogonal complement on the board, but it is in the notes. So the row space and the null space are orthogonal complements. Something we know about the Euclidean space Rn is that if you take any subspace of Rn and its orthogonal complement, the sum of those two spaces is all of Rn. Another interesting thing is the dimension of W plus the dimension of its orthogonal complement is n. Those two facts, along with this, give us these two things. The sum of the row space and the null space is Rn, and the rank plus the nullity is equal to n. This is called the rank plus nullity theorem. Theorem 264 talks about a square matrix, and it says that the following are equivalent. And the first thing is your matrix is invertible, and there is a long list of equivalent statements for a square matrix. In what follows, we're not assuming that A is a square matrix. Again, we're assuming it's an M by N matrix. The row space is a subspace of Rn, so is the null space. And again, to repeat, the sum of the two spaces is all of Rn. The column space is a subspace of Rm. The null space of A transpose is a subspace of Rm. So remember, the row space, the null space, the column space, and the null space of A transpose, these make the four fundamental subspaces of the matrix. Remember, the column space, the columns of A are the rows of A transpose, so the column space of A is the row space of A transpose. The row space of A transpose is an orthogonal complement to the null space of A transpose, so therefore the column space of A and the null space of A transpose are orthogonal complements to each other.